A very important concept in math is finding slopes of tangent lines to curves. When that curve is a circle, it's pretty easy to find the slope of the tangent line. Let's say this circle has radius 5, and this point over here is 3, 4. There's a rule that tangent line is always perpendicular to the radius in a circle. So if this radius has a slope of 4/3, then the tangent line is perpendicular to it. It has a slope of negative 3/4. But when the curve is not a circle, it can get pretty difficult. So here's an example of a parabola, y equals x squared, and we want to know the slope of the tangent line at the point 3, 9. Now a trick for doing this is to pick a point on the parabola that is to pick a point on the parabola to the right of 3, 9. Let's just say I come over here. Now that point is on the parabola. I'm going to draw. My picture's not as useful as I hoped. So this point over here, I'm going to call the distance, the difference between the x coordinates, I'm going to call that h. And it's a small number, presumably, so it's 3 plus h is the x coordinate. This is on the parabola, so the y coordinate is 3 plus h squared. Now, if h is not 0, this line is not a tangent line. It's called a secant line. But if I wanted, if the closer this second point is to the first point, the closer this thing is to being a tangent line. And even though the 2 points can't coincide, because you'd only have 1 point then, you would be able to make a line from that, we can figure out the slope by doing a limit. So it's the limit as h goes to 0 of the slope of this line segment. Well, what's the slope of this line segment? It's y2 minus y1. I'm going to write this as 3, 3 squared over x2 minus x1. So I'm using h here instead of x, because x already has a purpose. It's part of the function f of x equals x squared. So this is like a different function in terms of h. Depending on what h is, I could put any number in for h, actually. If I put 1 in for h, this would become the point 4, 16, and the slope would be 7. And that's what I would get if I plugged 1 in to this also. Now if I plug 0 into this, it would be 0 over 0. However, from a previous lesson, we've seen that if you actually do expand out the numerator, we get very lucky. The denominator just becomes h. And these 3 squares cancel out, and both of the terms on top have an h in them. This is still, by the way, limit as h goes to 0. Here also, limit as h goes to 0. It's annoying to have to keep writing that. The h's cancel out, and now you could actually plug 0 in for this h, and you get 6, which is the slope of that line segment. Now I can go more generally. If I call this point x, x squared instead of 3, 9, and call the other point x plus h, let's go like that. The other point is x plus h, x plus h squared. Then I can do the slope as the limit as h goes to 0, and the y coordinates are x plus h squared minus x squared, that's the other y coordinate, over x plus h minus x. Just like before, these x's cancel out. This numerator eventually becomes 2x h plus h squared. Again, limit h goes to 0. You can factor out the h, and you get 2x plus h. Those cancel out. And finally, you can plug 0 in for h, and you get 2x. So what this means is, remember when it was 3, 9? It meant we could expect the answer for the slope of the tangent line to be 2 times 3, which was 6. But now I can plug in anything else, like for instance, this is negative 1, comma 1. According to this formula, the slope of the tangent line is double the x-coordinate. Now we can go more generally. I'll skip to this. Suppose our equation was y equals x, or let's call it f of x equals x cubed. And this point here is x comma x cubed. This point to the right of it is x plus h comma x plus h cubed. And when I do the slope, so the slope is going to be the limit as h goes to 0, meaning this second point has got to get really, really close, ultimately close to that first point. And the slope is x plus h cubed minus x cubed, that's the y-coordinate of the second point, over x plus h minus x. That is the limit as h goes to 0. This is harder to expand. It becomes x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed. The bottom just becomes h. The x cubes cancel out here, and I can factor an h out of the numerator and get 3x squared plus 3x h plus h squared. Cancel out the h's. Then when you plug 0 in, these two things each turn into 0, and we're left with just 3x squared. So that means you could take any point on this y equals x cubed function, and if you want to know the slope of the tangent line, according to this, it's 3 times whatever the x-coordinate is squared, so the slope of this one at x equals 1 should be 3 times 1 squared, which is just 3. Here I have the function f of x equals 1 over x, this hyperbola. If I call this point x comma 1 over x, and this point to the right, this point to the right is x plus h comma 1 over x plus h. Then the slope will be the limit as h, approaches 0 of, this is going to be y2, this is going to be point 2, and this is going to be the first point. So it's y2 minus y1 over x2 minus x1. Those x's cancel out. The numerator, if we get common denominator of x times x plus h, we end up with x minus x plus h, which becomes, I'm going to keep writing a limit, h goes to 0. This turns into negative h over x times x plus h over h. This h can cancel out with this one. You could do that if you want by multiplying by the reciprocal. And we get negative 1 over x times x plus h. Finally, we can plug 0 in for h and get negative 1 over x squared. And that would tell me for any point. So I could pick any random point. For instance, this one is 3 1/3. Apparently the slope is negative 1/9 because it says 1 over the x-coordinate squared, and that is So that's not just the answer for this one question, but I can get the slope of the tangent line for any points on this curve. Here I have the function f of x equals square root of x. Here's the point x comma root x. Here's the other point, x plus h comma root x plus h. The slope is the limit as h goes to 0 of root x plus h minus root x over x plus h minus x. Those x's can cancel. This numerator, if we multiply top and bottom by root x plus h plus radical x, it looks like it's going to make it worse, but this times when you do a minus b times a plus b, you get a squared minus b squared. So this thing becomes x plus h minus x, which is just h. And the denominator is h times root x plus h plus root x. Then the h's cancel and you get 1 over this. Then you can plug 0 in for h and you get 1 over 2 root x. So if you take this line here, where x equals 3, the slope would be 1 over 2 root 3. And we can get the slope of the tangent line anywhere on that curve. Here I have f of x equals sine x. And for this one, our point is x comma sine x. And the point near it, that point is on the red curve, is x plus h comma sine x, comma sine x plus h, which makes the slope of the secant line in terms of h sine x plus h minus sine x over x plus h minus x. As h goes to 0, well, these x's cancel out. This we can expand with the sine a plus b formula. Sine x cosine h plus cosine x sine h minus sine x over h. And here's the slick trick. We group this and this together, and we factor out the sine x from it, so we get sine x cosine h minus 1 over h, and this term goes over the h also, plus cosine x sine h over h. Well, in a previous video I showed you, without a real proof, that sine h over h, that goes to 1 as h goes to 0, whereas cosine h minus 1 over h goes to 0 as h goes to 0. So that would mean that all that's left is cosine x. And that's real interesting. The slope of the tangent line is always the cosine of whatever the angle is. So in this case, if this is pi over 6, which is about 0.53, then the slope of this tangent line is going to be cosine pi over 6, which is radical 3 over 2. Here we have a cosine curve. So if I take this point over here and call it x plus h comma cosine x plus h, and this point here is x comma cosine x. Now the slope is going to be the limit as h goes to 0 of cosine x plus h minus cosine x over x plus h minus x. That always happens with the x's canceling out. We need to expand. Let's say limit h goes to 0. Cosine is cosine x cosine h minus sine x sine h. Then I have minus. Okay, I think we get to the same trick as before. This term and this term both have cosine x. So it's cosine x cosine h minus 1. That's a problem. No, that's okay. That's the thing we have from before. And then minus sine x sine h. I'll put these over h separately. That thing goes to 1. This thing goes to 0. So all that's left is negative sine x. So if my point were pi over 6, comma radical 3 over 2, then the slope of that tangent line would be negative sine pi over 6, which is negative 1/2. So what this process does is it gives us, if we do it, we could do it specifically for like a specific number, like we did over here. Did we ever do it? Yeah, we did it here for the 0.39. But even more powerful is to do it with general x comma x squared, or in this case, x comma x cubed. That way you end up with a formula that allows you to find the slope of the tangent line at any point on the curve. Now there are other curves besides these ones, but these are the sort of easiest ones to do, so we do it here in pre-calculus. Okay, that's it.